today's webinar, Unraveling Microscopic Mechanisms in Condensed Matter Systems with Local Magnetic Field Probes. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your audience console are multiple application widgets you can use. If you have a question for the speaker during the webcast, you can click on the Q&A widget at the bottom and submit your question. We will try to answer these during the webcast, but if a fuller answer is needed or we run out of time, it will be answered later via email. We do capture all questions. A copy of today's slide deck and additional materials are available in the resource list widget that looks like a green folder at the bottom of your screen. You can expand your slide area by clicking on the maximize icon at the top right of the slide area or by dragging the bottom right corner of the slide area. If you have any technical difficulty, please click on the help widget. It has a question mark icon and covers common technical issues. An on-demand version of this webcast will be available about 3 hours after the webcast, and you'll receive an email with a link to it. So I'm personally excited about today's webinar. I looked in my records and discovered I'd written about this field in 2004 in a story about a feat by Dan Ruger of IBM and his collaborators. They detected a single electron spin in a slab of glass. So it's quite amazing to see how far this field has gone since then. So our speakers are Martino Poggio of the University of Basel and Jelena Trbovic of Zurich Instruments. So please start, Martino.
Thank you very much, Charles, for the introduction. So today I want to tell you about efforts in my lab and around the world to image weak magnetic field patterns on the nanometer scale and how we can use these tools to decipher the mechanisms behind a variety of new and poorly understood condensed matter phenomena. So I'm pleased to do this together with Jelena, who I've known since a long time, since she was a researcher here at the University of Basel. And I'm also very pleased to be doing this together with Zurich Instruments, because actually since I started my lab here in Basel, Zurich Instruments devices have been really important to our research. We've been profiting from them for over 10 years. Back in 2009, when I started the lab, actually we were doing very sensitive magnetic resonance force microscopy experiments, similar to what Charles was referring to from Dan Ruger, and the Zurich lock-in with its completely digital basis was allowing us to simultaneously measure the same signal with many different time constants, and essentially allowed us to extract a correlation time of signals on the fly. And this allowed me to basically see me and people in my group, to see whether we were really just measuring noise or whether we were measuring the spin noise that we were looking for. Okay, so without further ado, let me move on to today's topic. I want to talk about magnetic imaging. And this is a picture from the early 1800s, where you see an image of stray magnetic fields around permanent magnets. And it was really images like this, images of fields around permanent magnets, current-carrying wires, made with tiny iron filings that played a crucial role in the development of the theory of electromagnetism at that time, and basically provided the impetus for the development of Maxwell's equations and ultimately the whole revolution that followed. Today, magnetic imaging techniques continue to provide invaluable insights well beyond providing pictures. So they shed light on magnetization patterns, spin configurations, current distributions, which are normally invisible in optical or topographic images. So unlike bulk measurements of transport or magnetization, susceptibility or heat capacity, these kinds of images provide microscopic information about length scales, inhomogeneity, interactions. And this is really important because macroscopic manifestations of quantum mechanics, especially involving strongly correlated states like superconductivity and magnetism, they're really sensitive to the local environment. And in many cases, a nanometer scale spatial resolution is required in order to investigate these states and in order to identify the conditions for their emergence. So this is an example of kind of modern magnetic imaging of spin polarized scanning tunneling spectroscopy of some cobalt islands, where you essentially see the magnetism of these cobalt islands on the atomic scale. Just to give another example, this is an example of a magneto-optical image of local spin polarization, so using a Kerr microscope. This is back from 2004 from the Ausschelom group, where they first revealed essentially the spin polarization produced by the spin Hall effect of a current that's essentially flowing vertically in this picture through this channel of gallium arsenide, and you see the opposite spin polarization accumulating at the edges. This is a more recent example from 2010, where a Lorentz microscope, so another method for nanometer scale magnetic imaging, is revealing the existence of nanometer scale magnetization configurations known as magnetic skyrmions, which turn out to be topologically protected, and it was doing so for the first time. And this essentially started a whole field investigating these magnetic skyrmions and their potential applications. And without these kinds of images, you could really not tell whether these are really there or not. As a final example, I want to show this SQUID microscopy image of basically edge currents flowing through a topological insulator. So what you can see here is basically that the scanning magnetic imaging technique reveals the fact that currents in this topological insulator are flowing on the surface and on the edges under certain gate voltage conditions. This kind of leads me to my main point here, which is that, magnetic imaging techniques can kind of be divided into two different categories, those that are sensitive to magnetization and those that are sensitive to stray magnetic field. So basically, magnetization mapping techniques include the example of the spin polarized scanning tunneling spectroscopy that I showed in the beginning, the magneto-optical microscopy, and the Lorentz microscopy. And these are direct measurements of magnetization. And they're very attractive for investigating magnetic domains and spin textures, but they have some restrictions into what kind of samples and conditions that they can be applied to. On the other hand, a measurement like this one makes measurements of stray magnetic field, and from this stray magnetic field you can infer, say, what's going on with flowing currents or with magnetization underneath. And these are applicable to a much wider set of phenomena. And the stray fields can be produced not only by magnetization patterns, but as I said, current distributions, and the samples that you can measure can span across conductors, insulators, soft biological matter, and a whole variety of other things. So anything which produces a magnetic field. And the common methods for this are, what I showed in the beginning, using a fine magnetic powder as demonstrated by in the 1800s and later improved by Bitter, Lorentz microscopy, electron holography, and a number of scanning probe techniques. In this talk, I want to focus on the foremost of these scanning probe techniques that are measuring a stray magnetic field, and these are magnetic force microscopy, or MF-M, scanning superconducting quantum interference device microscopy, or scanning SQUID, and scanning nitrogen-vacancy center microscopy. And I focus on these because these are the techniques which combine the highest sensitivity and the highest spatial resolution, and are really what can give us a view into some of the new physics that's coming out. Okay. So, and what is that new physics? Well, basically, there's an explosion in the last decade or so of 2D materials. Many of us are familiar with graphene and other similar 2D materials that you can see kind of on the slide. These kinds of materials can be metallic, semiconducting, insulating. They can have a whole variety of properties. And what's really nice about these is that you can essentially, through van der Waals engineering, you can stack these things on top of each other and engineer new material properties, new band structures in a very, very flexible and controllable way. And this field is really exploding at the moment. And in order to understand what's going on in these materials, what we really need are these scanning probe microscopies, specifically scanning magnetic probe microscopies that can elucidate what's going on with magnetization and currents in these samples. So here's just another slide to show you what can be done with these kinds of 2D materials, what kind of heterostructures can be built up. You can not only stack different atomic layers of, say, graphene, the same material on top of each other, but you can do different materials on top of each other, and you can even control the angle, the relative angle with which you stack these on top of each other, and therefore finely tune the band structure and other material properties. And so this is opening a huge playground for physicists, but in order to properly investigate this, we really need to have sensitive scanning probe microscopies. Okay, so to give you an idea of what's happening just in the last 2 or 3 years, a number of correlated states, such as superconductivity, mod-insulating states, and magnetically ordered states have been observed in these kinds of materials, and they're just now beginning to be understood. So there's really an urgent need for sensitive and high resolution SPM, scanning probe microscopy, to zero in on the nanometer scale mechanism behind these phenomena and to understand the role of disorder and lateral confinement in these materials. So on the left, you see the paper, one of the papers showing basically superconducting properties in twisted bilayer graphene, and on the right, you see some experiments showing 2D magnetism in some 2D magnetic samples. Okay, so how do we decipher the mechanisms behind these phenomena? Well, as I said, we need sensitive scanning magnetic probes. So what we need are scanning magnetic probes that can really measure weak magnetic fields and at a high spatial resolution in order to overcome inhomogeneity by measuring local fields really at a local level. And so what we're going to discuss are mostly techniques that reside on the sort of top left side of this graph, where you have the highest resolution, so where the dimension of the sensor is the smallest and the potential for high resolution is the highest, and where you still have quite a good magnetic field sensitivity. And if you look carefully at those little icons from this review paper, you'll see that those essentially involve scanning probe microscopies of the type that I mentioned, so magnetic force microscopy, scanning SQUID microscopy, and scanning nitrogen-vacancy center microscopy. Okay, so here finally an outline of my talk. I'm going to talk about scanning SQUID microscopy first, then Jelena will tell a little bit about how you can use lock-ins to make the measurements that I'm discussing. Then I will talk about magnetic force microscopy, and finally I'll try to make a comparison between the techniques and talk a little bit about what needs to be done in the future. So what is a scanning SQUID, or what is a SQUID? Well, as many of you know, this was first developed in the 1980s, and it's one of the first quantum sensors that was developed. And it essentially measures magnetic flux through threading through a superconducting loop, because this magnetic flux produces an Aronoff-Bohm phase on the superconducting wave function. And in the SQUID, this phase is then detected in a circuit which includes 2 Josephson junctions. And here these Josephson junctions are shown as these kind of weak links in the loop. And this results in an extremely sensitive measure of the magnetic flux, which, as you can see in a little plot, is periodic in the flux quantum. Okay, these SQUIDs have been around, as I said, for many, many years, and scanning SQUIDs have also been around for many years. And there's a cartoon of this from an old paper showing the different kinds of modalities of scanning SQUID. You can essentially scan the superconducting SQUID loop, or you can scan a pickup loop, which is inductively coupled to that SQUID, or you can do some combination of both. Recently, in about the last decade or so, this scheme, there was a new scheme developed to get the kind of best combined sensitivity and spatial resolution, and it was pioneered at the Weizmann Institute in Israel. Essentially, it involves producing a SQUID loop right at the end of a very, very sharp quartz tip, and that's what you see in this figure here. You see an aluminum SQUID, which is produced at the very end of a very sharp tip, and through the clever processing, you can produce 2 Josephson junctions and a superconducting loop. Actually, we've learned how to make these in our own lab. Actually, we make them out of lead these days, and you can see an example of one of these on the left side of this foil. And these get to have field sensitivities on the order of a few nanotesla per root hertz, and they can have diameters down to 50 nanometers, more typically around 100 nanometers, meaning that that's the kind of spatial resolution you can get with this scanning probe. These scanning SQUIDs are also very interesting because they are excellent sensors of temperature. As you can see in this slide, they have a sensitivity on the order of 1 microkelvin per root hertz by virtue of the fact that they have Josephson junctions that you can bring in very close proximity to a measured sample, and therefore in a kind of local thermal contact with that sample. And so actually you can measure both magnetic and thermal signals using this scanning probe. And actually you can use the Zurich lock-in to do this simultaneously in a very nice way. Because the magnetic signal depends, let's say, linearly on some current. Let's say you're trying to measure a current through a sample. The magnetic signal, the Biot-Savart field, depends linearly linearly on the current, and the temperature change depends quadratically on that, then if you have, you can basically use this property to look at the signal at either at the first harmonic of the drive signal or at the second harmonic of the drive signal. And using the Zurich Instruments lock-in, you can look at these two harmonics at the same time and therefore do a scanning probe, which gives you both temperature and magnetic field information at the same time. Okay, so let me tell you a little bit about what you can do with these scanning squids. So this is a cartoon of one of these scanning squids over a magnetic sample. In this case, this is a sample of magnetic spin ice. So these are arrays of nanomagnets put together in a chiral fashion to create magnetic frustration. And what we do is essentially locally measure the stray field of these arrays, and we can see how the local field depends as we bring this array through reversal. This is, of course, a cartoon of what this experiment looks like for all of you students out there. What this actually looks like is more what you see in this slide. So this is happening in a lab, a very crowded lab, as you see in this slide, inside one of these helium cryostats. And inside one of those helium cryostats, we have a custom-built scanning probe, which is hanging from some springs for vibration isolation, contains a number of piezoelectric motors for moving around, and ultimately allows you to scan this very sharp scanning squid over a sample. And so these are the kinds of experiments that you can do, the kind of data that you can measure. On the top row, what you see is the stray field from these individual nanomagnets as we send the array through magnetic reversal. And you can essentially compare these stray field patterns with what simulations tell you. And with very careful comparisons, what we could do is determine that the nanomagnets don't behave as macrospins, but themselves have very significant magnetization texture, and that ultimately this magnetization texture affects the behavior of the whole array. So this is some very important information that you can only get from a local probe. This is another example of something that you can do with this scanning probe. So we measure stray fields from superconducting vortices in a thin film of molybdenum silicide. This is a material that's used for superconducting nanowire single photon detectors. And in these photon detectors, essentially, the fact that photons create magnetic vortices or superconducting vortices is used to detect the photons. But the mechanism behind this is not very well understood, so there's a lot of interest in trying to study the dynamics and the pinning of these vortices within these thin films. And you can see here in these movies very clearly that the SQUID allows you to see the dynamics of these vortices and even to see the strength of the pinning sites and how defects affect these pinning sites. This is another example from a different group, not my own group, from the group of Ellie Zeldorf and the Weizmann Institute, where you can see superconducting vortices in a thin lead film, a superconducting film. And what you can see as you go from left to right in these images is that the current is being increased along the vertical direction. And as you increase the current, what you can see is that by Lorentz force, the vortices are pushed towards the right side of the slide. And at some point, they get pushed so hard that they traverse the entire superconductor and start flowing across the superconductor and breaking superconductivity in this kind of branched flow that you see here. And it turns out you can relate this branching flow very nicely to what you measure in macroscopic measurements of the breaking of superconductivity. Each branch essentially results in a step change in the effective resistance of this superconductor. And this really gives you a kind of microscopic picture of what's going on when the current in a superconductor gets very high and approaches the critical current. Here's another experiment that you can do on measuring vortices in superconductors. So here we've taken in our own lab samples from the Wallraff group at ETH Zurich. These are samples that are superconducting qubits used for quantum computation. And the researchers in the Wallraff group are interested to know how currents exactly flow through their circuits so that they can optimally design these circuits in order to couple better to certain qubits and to avoid cross-coupling between qubits. So our task here was essentially to scan over these superconducting devices and try to map out how currents flow. And you can see an example of that. So we zoom in on this single superconducting qubit, which is essentially a SQUID, and we zoom in on the modulation line, which is the kind of structure that you see at on the bottom half of this slide. And when we image that the stray fields coming from currents flowing through that modulation line, we can then reconstruct the exact distribution of the current density in 2 dimensions and really see how the current flows, and we can help the quantum engineers in the WALREF group better engineer their qubits in order to improve their coupling and reduce their cross couplings. Finally, I want to show you some beautiful experiments from the Zeldov group using these scanning squids on graphene, where you can really see the effect of the quantum Hall edge currents in graphene. These are some of the first images of quantum Hall edge currents, even though the quantum Hall effect has been around for so long. And what they can see is that as you increase change the density of the system, you can see topological channels of edge currents coming from the quantum Hall effect shown in this slide here. So as I increase the gate voltage here, I go back and forth and I see these topological edge channels, and that's not terribly surprising. That's exactly what is predicted by the quantum Hall effect. But what we see that was not predicted, is not generally understood, is that there are also non-topological currents flowing in the opposite direction. So this scanning squid has really revealed something rather new about a very, very old effect. And yeah, just finally here, another scanning squid microscopy experiment from the Zeldov group showing essentially the twist angle disorder in twisted bilayer graphene, and really showing how much disorder there is in these systems. And these images that you see here show you in the kind of brownish where the system is in a superconducting state, so where the twist angle is really at the magic angle. And these patches are really just barely connected. So it really shows that it's almost a miracle that these systems in macroscopic measurements of transport show superconductivity, because there really is so much disorder in there. And in order to understand this, you really need, again, local magnetic scanning probes. Okay, so I want to hand off now to Jelena, who's going to talk a little bit about the Zurich Instruments lock-in amplifiers, and then I'll come back and talk about magnetic force microscopy. So, Jelena, here's your slide.
Thanks, Martino. Thanks a lot for this. So what I'm going to try and do in next about 15 minutes is to help you understand how Zurich Instruments lock-ins enable the discoveries that Martino has shown, and also give you a bit of a background into some of the measurements he will show later in the second part of the talk. And in order to do that, it's first very important to understand how we build our instruments, that they consist of 2 main parts. They consist of hardware, which consists of carefully designed analog front end, behind which an FPGA board sits and allows the adequate speed and handling of the digitized data, so that finally you end up with high sensitivity, high resolution, and low noise instrumentation. And on top of that, we built a user interface and software that allows the researchers to have efficient work during their experiments, to look at the signals from various angles from time and frequency domain. And also the FPGA board allows us to program different functionalities and features, and something that you can always add so your instrument can grow together with your research. And with that, we have built a number of different instruments aimed at different applications. For example, quantum control systems, lock-in amplifiers are very general instruments, and boxcar averagers and impedance analyzers for more specific tasks that you want to do. So now the Zurich Instruments provide 3 types of lock-in amplifiers. On top you see MF-LI that goes from DC to 500 kilohertz and to 5 megahertz. In the middle you see dual lock-in amplifier HF2LI that goes to 50 megahertz, and on the bottom we can see 600 megahertz UHF-LI that's also dual lock-in. And all these instruments have Lab1 user interface as a single cockpit, where they can see not only the lock-in results and work, but they can also see the raw signal in the scope, then they can use the sweeper, the plotter, and also the advanced tools such as PID, PLL controllers, and multi-frequency options. So all these are available for advanced use. So let's see when it's actually very important to use lock-in amplifiers, and that's when the signal is so small, and these are the situations in the research when we don't really know what to expect, and we have a lot of noise that comes not just from our sample. The noise picture that's very important also comes from the setup and also from the instruments that we use to measure. And there, what's very important is to, first of all, understand what lock-in amplifiers measure, and that's the amplitude and the phase of the signal with respect to a reference that's always available for the lock-in, be it internally or externally given. So let's see how the amplitude and phase are measured. We start from the signal that comes together with the noise, and then we compare it to reference signal, and in a process called demodulation, which starts with mixing, which is literally multiplying the signal and the reference, and then it projects this product onto two axes, one in phase and one out of phase with the reference. And when this is done exactly at when signal and reference have the same frequencies, you can get these two terms. One that's independent of time, and the other that contains the 2 omega component of your signal. And this is something that we want to get rid of, and we do it by using the filtering. And when this is done successfully, we end up only with the X and Y components of the signal, from which we can calculate easily the amplitude and the phase. So now filtering is a very important part of getting the right result from the lock-in, and we usually see it as a time constant of the filter. We also see it as a filter bandwidth. So what this means is that if we have a large filter bandwidth, we admit more noise. You can see in the graph on the right, with very large filter bandwidth and low time constant, the signal is surrounded by noise, but as we reduce the filter bandwidth further, we increase the time constants, we have less noise, but we also slow down the measurement. Another thing that you can do in order to increase the signal to noise ratio is to add more filter orders in this filter chain. However, you need to be careful when sampling the results after increasing the filter order, for example, as you can get erroneous signals measured. So for example, if you start off with a second order filter, the red curve, and it's enough to use about five time constants to sample the result, and then you switch to the fourth filter order, and there you see that only 10 time constants are good for this choice of the filter. Otherwise, you would read about 70% of the signal value. So this is something you need to have in mind. Finally, what's important when choosing your instrument is actually knowing that it also contributes to the noise of your measurement. Noise of your measurement. I'm trying to go back here. So what's important is to make sure that the input noise is low enough. That the input noise is low enough that that it's low enough so we can measure the small signals, and also that the noise coming from the lock-in doesn't influence the electronic temperature, for example, in low temperature experiments. So here, when you actually come to do the experiment, you can start off with a simple lock-in that has one demodulator, one external reference, and you have to choose between voltage or current measurement at the single frequency. However, as Martino has mentioned, if you use the, I can't if you use the multi-demodulator option that I'm trying to switch to, here it is, you can have 4 dual phase demodulators that you can then use to measure the DC signal, the fundamental, the higher harmonic, all these things that Martino has mentioned that can be used in these measurements. So here's an example of 4 signals measured at the same time. So on the left you see the scope picture, and on the right you see these 4 signals measured at the same time. We see amplitude and phase in the plotter. Now, when the signal that lock-in measures is actually a resonance of a sensor or a multiple tones of this sensor, it is tasked of the lock-in not just to measure the amplitude and phase, but also to control and lock onto the resonance frequency of these sensors. And for this, you can use available tools like Sweeper, first of all, to characterize the sensor, then find which phase do you need to provide to the phase lock loop to lock onto this signal. And we can see here that with the MF-MD option that has multiple demodulators and PID control, you can track these two resonances at the same time, and lock-in will measure the shift from the resonance frequency, and that will be used as a signal that corresponds to the surrounding magnetic field components. And so to summarize here, so all these things put together in a single device will allow you to have a very, very smooth experiment operation. You can measure several of these parameters at the same time. You can control the resonances that you use for sensing. And this is exactly what Martino will be using for the remainder of the talk. Martino, I'll hand it over to you.
Thank you very much, Jelena. Yeah, so I'm going to continue now and talk about magnetic force microscopy as another high sensitive and nanometer scale magnetic imaging technique. So MFM was developed in the late 80s in the immediate aftermath of the invention of the STM and the AFM, and it's basically now a standard scanning probe technique. It essentially involves a cantilever, which is hundreds of microns in size, typically, with a very sharp magnetic tip. And the interactions of this tip with the sample of interest have an effect on the cantilever frequency and the amplitude, just like in AFM. And this gives you a magnetic contrast. And in the best case, you can achieve resolutions on the order of 10 nanometers in very special cases, as shown here in an example from the WHO group at EMPA here in Switzerland. In general, resolutions are more on the order of 100 nanometers or so. It is not an especially sensitive technique to small fields, and it can be highly invasive because of the highly magnetic tip. It's basically intended more for strongly magnetic samples and high spatial resolution. Okay, but in fact, you can, if you just work on the mechanical transducer side and try to use transducers which are softer, basically sensitive to smaller magnetic forces and magnetic force gradients, you can make an MFM which is able to image more subtle magnetic field patterns and is more sensitive. So ultimately, the sensitivity of a mechanical transducer, like the one that I'm showing here, used basically back in the Rugar lab at IBM to do magnetic resonance force microscopy and other very, very sensitive force detection techniques. The sensitivity of this is determined by its thermal motion, by its Brownian motion. And you can see a relation for that here. Essentially, this motion is shown as a spectral force density, a white spectral force density in the top of the slide. It essentially depends on the temperature, the Boltzmann constant, and this factor gamma, which is the mechanical dissipation or the friction of the mechanical system. So if you want to make a more sensitive force sensor, be it an MFM or any other kind of force sensor, you need to go to lower temperatures and you need to reduce this friction. And if you can do that, then you can measure all kinds of ways via amplitude or frequency measurements, much smaller forces, much smaller torques, smaller force gradients, smaller torque gradients. And if you just look at this kind of structure, actually it turns out that many of the parameters in this factor gamma, so the mass of the object, the resonant frequency, the Q, they vary relatively simply on the dimensions of this, say, cantilever sensor that you're using. And it turns out that if you scale this cantilever down and you make it very long and thin and just make it smaller, you can reduce the dissipation and therefore have a higher force sensitivity, so a better force sensitivity. At the same time, what tends to happen is that the frequency of the object, as you scale it down, the resonant frequency of the mechanical object goes up, which is also very nice because it allows you to avoid low frequency noise like 1/f noise. So this has kind of pushed the field of nanomechanical sensing to go to smaller and smaller mechanical transducers, smaller and smaller AFM, MFM transducers. And so we've been going as a, say, community from top-down devices like that silicon cantilever I showed you, or the standard AFM, MFM cantilever, towards things like nanowires, nanotubes, very small mechanical objects that are typically grown from the bottom up. And this is just a big table from a recent review that I wrote with a colleague of mine of all the nanowires that have been used and their properties. And it turns out that they have very good mechanical properties. Detecting their motion is not as hard as you might expect, and they can really improve force sensing sensitivities going forward. So just to show you how a nanowire force sensor might look, this is an example from my own lab. So we get these particular nanowires from collaborators in the EPF of Lausanne. These are from the Fontcomberta group, gallium arsenide nanowires grown in MBE, and you can see them growing out of a wafer in this slide. We then take these nanowires, and if you can see in this slide, we essentially hang them from a piezoelectric stage, and we scan them in the pendulum geometry above a sample, and we use them as kind of force sensors detecting the tip sample forces. And in order to do that, we have to basically detect their deflection very accurately using an optical interferometer that you see in this cartoon here. Again, for all those students out there, what this really looks like is shown here. So we have a custom-built microscope that looks a lot like the one we use in the SQUID experiments, where we have some piezoelectric movers, some, in this case, fiber optics to do the detection of the nanowire motion. And all of this allows us to very precisely scan these nanowires on top of a sample. Nanowires are very interesting. Any kind of very long and thin and symmetric object like this always has two nearly degenerate flexural modes, and these can be used to sense forces in different directions at the same time. So what you'll have with this kind of nanowire is that it has two flexural modes that oscillate in perpendicular directions, and you can detect them with this optical interferometer. And if you do so, what you'll see, let's say in your Zurich Instruments spectrum analyzer, you'll see two flexural mode peaks corresponding to these two orthogonal flexural modes and the motion in these two orthogonal directions. And if you can monitor the frequency and amplitude of these peaks, you can essentially monitor the forces and force gradients along these two perpendicular directions. So what you essentially have, especially using the Zurich lock-in, which allows you to follow these two frequencies with two independent PLLs simultaneously, is a kind of a force compass. So a little nanowire which you scan over your sample and allows you to measure force magnitude and direction of the tip sample forces. And therefore, you can produce pictures like what you've seen here. So this is just a proof of concept experiment we did some years ago in our lab, where you can see electrostatic and dielectric forces mapped out using one of these kind of nanowire compasses or nanowire force sensors. And you can see that the experiments very nicely match what you would expect for these kinds of forces, and that confirms that they work rather nicely. What's very nice about this is not only that you have this directional information, but that you're measuring really tiny forces, much tinier forces than are normally measured by such by atomic force microscopes or magnetic force microscopes. In order to bring this back to what I was originally talking about, so magnetic imaging, we need to functionalize these nanowire force sensors with a magnetic tip in order to make a kind of nanowire MFM. And this should give us a very, very sensitive version of MFM. And so with some collaborators at the University of Regensburg, we did some work trying to put magnetic tips on the end of gallium arsenide nanowires. What you see here is a manganese arsenide ball, a little magnetic tip grown in an MBE on the end of a gallium arsenide nanowire, and this provides a really nice point-like MFM. And just to show you how this actually works, what you can do is use these to measure a known field and see how sensitively you can measure that field. So in this particular experiment, by passing a current through this gold-colored wire and scanning our nanowire on top of it, we could measure the Biot-Savart field of that current. And by just turning the current down, we could reduce the amplitude of that field and see when our sensor stopped detecting the field. So essentially, we could see when, what the sensitivity limit of our sensor was, and ultimately, this gave us the answer that these nanowires are really very sensitive to magnetic field gradient, and they're competitive with the scanning SQUID sensors and other state-of-the-art sensors. And just to give you an idea of that, so these are an example of two different types of nanowire magnetic force microscope sensors that we've tested. One is this manganese arsenide tipped nanowire that I just showed you on the left. That one turns out to be sensitive to kind of few millitesla per meter of magnetic force gradient. So that's on the order of 1,000 times more sensitive than a standard MFM. And this other nanowire that you've seen, that you can see here, which is fully magnetic, it's a fully magnetic wire of cobalt, is actually sensitive to magnetic field on the level of a few nanotesla per root hertz, which is really on the same order of what you can do with the best SQUIDs and other sensors. So these are really very promising. They're at an early stage, but they could also contribute to this growing field of nanometer scale sensitive magnetic sensing. And just to show you that you can also make pictures with these, I want to show this slide here where we've essentially made a magnetic force microscope image with these magnetic nanowires over a permalloy disk, and you can see that we can measure essentially the magnetic stray fields of this permalloy disk when it's in a vortex state, and that what we measure very nicely matches what we simulate, so that we can already make nanometer scale images using this technique. Okay, so I've talked about MFM, I've talked about scanning SQUID. I should also talk about scanning nitrogen-vacancy center microscopy, which is really the third most sensitive and highest resolution technique. It's not something that we work on in our own group, so I'm going to talk about it a bit less, but it's certainly an extremely important and growing technique that really allows you to investigate 2D materials in interesting ways. The way this works is essentially you have a nitrogen vacancy, which is a defect in diamond, and you implant that at the tip of a scanning probe, and you basically scan this over your sample as shown in this cartoon. And this nitrogen vacancy essentially acts as a kind of a spin probe that you can optically measure, and you can optically measure its spin state and therefore get information about the magnetic field. So essentially by measuring the splitting of this defect spin, the energy splitting, you can measure the local field at that atomic position. Now, this is really a very attractive technique because these defects can be implanted really very close to the surface of the tip, meaning that this sort of effective sensor size can be very small, on the order of 10 nanometers, really one of the smallest effective sensor sizes that you can have. And it is very, very sensitive. It can reach down to 100 nanotesla per root hertz. So again, competitive with the other techniques that we've been discussing. And these can be applied, as I say, because it's a measurement of the stray field, to measuring currents. And you see an example from the Degen lab at the ETH in Zurich here, where a scanning NV center was used to image currents flowing through patterned wires and nanotubes on a surface, essentially by measuring the Biot-Savart field and then doing a deconvolution to get back what the flowing current was. And they can also be used to measure magnetization. This is an example from the Malatinsky group, also here in Switzerland, but here at the University of Basel, where they used scanning NV microscopy to image 2D magnets. So this is a 2D magnet, chromium iodine 3, which is a layered magnet where you really see the effect on the magnetism of the layers, where essentially the magnetism changes sign as you put one layer on top of another, and you can very, very clearly see that in these beautiful scanning probe images. Right, so that was NV center, scanning NV center microscopy. I talked about MFM. I talked about scanning SQUID in the beginning. These are the kind of three techniques that I think are the best positioned to investigate all of these great new 2D materials. And in this foil, I want to kind of show you how this should work. So essentially, we want to learn about current density and magnetization in these 2D materials. These kinds of contrasts produce a stray field, a magnetic field B, which we can then measure using the various techniques. And the various techniques actually measure various slightly different quantities. So the scanning SQUID measures magnetic flux, meaning the field integrated over the loop area. The MFM measures magnetic field derivative along a certain direction, and the scanning NV center measures actually one component of the magnetic field along the quantization axis. All of these are slightly different, and the way that the fields fall off depends slightly differently on the type of contrast. So it's important to understand this in order to select the right technique for the right experiment. And I want to show a little bit about that in the next couple slides. So you can see here a comparison of kind of the best state-of-the-art scanning probe microscopies of these three to different, and their sensitivity to the different types of contrast. So here I show it in terms of the sensitivity to current. What you can see is that standard MFM is really not very sensitive. NV magnetometry, as you approach the surface, it's the type of technique where you can get closest to the surface, and because it's essentially the one with the smallest effective size, and ultimately is the best if you want high resolution imaging. But you can see that scanning SQUID, if you're interested in things that are kind of 10 nanometers or bigger, is the most sensitive technique. And nanowire MFM has a potential to be very interesting for larger feature sizes, although it's as yet still unproven. If you then look at magnetization, the picture is slightly different. Again, standard MFM is really far too weak to measure very, very small magnetic concentrations of magnetic moment, but nanowire MFM might make it competitive with the other two techniques. Scanning SQUID, again, and NV center microscopy are kind of similar when you look at if you're not interested in resolutions better than 10 nanometers. If you want to get closer than 10 nanometers, then NV center microscopy appears to be the only way to go, and even there that might be difficult. Another way to look at this is in this plot. So I have here, I'm essentially plotting characteristic size of the sensor on the y-axis against the magnetic field noise, characteristic magnetic field noise of that type of sensor on the x-axis. And I've plotted a few of the kind of state-of-the-art scanning SQUIDs in red, the MFM, including nanowire MFM in blue, and scanning NV magnetometry in green. And what you can see is that the NV magnetometry really combines the smallest sensor size with the highest sensitivity, whereas scanning SQUID is really the highest sensitivity in terms of so lowest magnetic field noise, but you pay with the size of the sensor. And MFM and maybe nanowire MFM is somewhere in between. If you then overlay this with what you need to do in order to measure, say, magnetic moments, that's represented by these diagonal lines. So to measure 1 Bohr magneton per root hertz, you need to get over that dotted line. To measure 1 nuclear magneton, you need to get over that solid line. And you can see that scanning SQUID is really positioned very well. Scanning NV magnetometry is positioned really very well for magnetic moment, because the fields generated by magnetic moments fall off so quickly with distance, so one over the cube of the distance. On the other hand, if you're interested in current contrast, you can see that it falls off much less quickly, so it falls off as 1 over r, distance from the sample, and therefore scanning SQUID magnetometry and MFM become much more attractive, especially if you're not interested in extremely high spatial resolutions. So you have to consider a little bit what you're measuring in your 2D material or other sample, and match this with the correct technique. Okay, so in my own group, we've been working a lot on nanowires, as I've talked about. We're also working on scanning SQUIDs and trying to improve them and combine them with the force microscopy centers. So here's an example of some recent work we're trying to do, where we're trying to make SQUIDs at the tips of scanning, at the tips of atomic force microscope cantilevers, and this is part of a collaboration that we're leading here in Basel between our own group, the group of Jose Maria de Teresa in Zaragoza, the group of Dieter Kolle in Tübingen, and the group of Armin Knoll at the IBM in Zurich. And we're hoping that in the next few years, as this collaboration goes forward, that we can create even better magnetic imaging sensors for nanometer scale experiments. So with that, I will stop talking. I want to thank all the people in my group who contributed to most of what I showed you today, the funding agencies for supporting us, and finally you for your kind attention. Thank you.
Thanks, Martino. We have a whole bunch of questions, so I'll start right away. Is it possible in principle to put the nanowire tip?
Excuse me, can you repeat the question? So I think I understood, is it possible to make a nanowire tip? Is that right?
I can't hear Charles.
Oh, okay, I see in the chat that maybe we lost Charles. Well, I could try to say something. I could infer what the question was. Perhaps the question was, can we make the nanowire tips sharper? And certainly that's something that would help with the spatial resolution and something that we're working on. This heavily depends on the type of nanowire that you have and the way that you produce the nanowire. And I think one of the more promising methods for producing sharp nanowire tips is this technique that I just very briefly showed in the slides. So we had some fully magnetic nanowires made of cobalt using a technique called focused ion beam induced deposition. And using these kinds of techniques, you could improve the sharpness much beyond the kind of what we've had until now, which is a tip size of order 100 nanometers, probably down to the kind of 20 nanometer range.
So I guess if we don't hear from Charles, Martino, maybe I can ask you one question.
Yes.
And that is, have you compared transport with local probing in any of these samples to be able to see the difference?
So we have done that. Maybe I can show. I don't have a slide for that, but I can show an example from the Zeldorf group in the Weizmann, where they did something very nice like that. I was alluding to this experiment in my talk, where they essentially have a current flowing through a lead film, and you can see what happens to the vortices. They get pushed to the side as you increase the current, going from left to right on the slide, and eventually they start essentially flowing through the sample, and that indicates a break in the superconductivity. So essentially, superconductivity is broken when one of those channels crosses all the way the sample, and it turns out that each one of those channels corresponds to a step in the macroscopic transport that you measure, so in the effective resistance that you measure. So you can, it's in this paper, if you look it up, you can see a very nice correlation between the kind of local imaging and the macroscopic transport, and I think there's a lot more that you can do in similar experiments on 2D materials, comparing the transport and the scanning probe measurements at the same time.
Mm-hmm. So I've got another question for you to do with your slide 24 and the imaging of superconducting qubits. So it's in two parts, so I'll ask them one after the other. So is the scanning SQUID method frequency dependent?
Right, very good. Yes, so in fact, the bandwidth of the SQUID device itself is very, very high. I mean, you should be able to go maybe up to gigahertz or so. But with all the amplifiers and things that we have, we're kind of limited to the tens of kilohertz, maybe 100 kilohertz or so. And so, yes, we can't pick up the very, very high frequencies that are involved in the actual, in the running of the qubits. So we do these experiments at quite a bit lower frequencies. In principle, you could imagine doing the imaging if you redesign the scanning probe system at these higher frequencies, but it would involve quite some effort. And for now, we've kind of concentrated on what happens at lower frequencies.
So this is probably a question you faced before. Can the techniques you've talked about be implemented in a liquid medium or soft matter, for that matter?
Right. Yes, so for the scanning squids, as the ones that I've presented, the squid on tips, I would see that it's very difficult, especially the lead ones. They oxidize. They need to be in vacuum in order to work. Of course, they need to be at extremely low temperature, so below the critical temperature. So I think for any kind of squid, that would be difficult. For the diamond sensors that I showed, I think I'm not aware of them working in liquid, but I don't see any reason why they shouldn't be able to. So they can work in ambient conditions also without vacuum. Certainly the sensitivity may not be as good as you would have at low temperature. And the MFM, of course, does. So standard MFM can work in liquid and in ambient conditions. And nanowire MFM hasn't been shown to work under those conditions, but in principle, with the right sensors, this could also work. Certainly the sensitivities will be different. You will have much more dissipation. You won't be limited by Brownian motion of the sensor anymore, but you'll probably be limited by effects of the liquid environment. But it should be in principle possible.
We had a question about the resolution of nitrogen-vacancy spectroscopy. So what's the highest resolution that can be achieved? And with that resolution, is it possible to measure the shallow magnetic field from the twisted bismuth layer graphene using it?
So as far as I'm aware, the highest resolution that's been shown is on the order of... Sorry?
Sorry, I misled the question. It's bilayer graphene using it.
Yeah. So as far as I'm aware, the highest resolution, spatial resolution for NV has been about 25 nanometers. In principle, the NV can be implanted below the surface of the tip by about 10 nanometers. So you can imagine resolutions of that order, but probably not better. Certainly people are working on implanting them a little bit less deep, but usually what happens is that the coherence of these NVs suffers when they get closer to the surface, and then therefore their magnetic sensitivity goes down. So it may not be so easy to go to higher resolutions than 10 nanometers. Has it been used to measure the stray fields from twisted bilayer graphene? I'm not sure. I think there have been some attempts. Because some of the sizes of currents that you can pass through there are rather limited, it may be difficult to use scanning NV center microscopy. So it is less sensitive to currents than the other two techniques, as I tried to show, and therefore most current imaging that I've seen with NVs involves kind of microamps of currents, and those are rather large for, say, mesoscopic transport experiments.
We have an interesting question about industrial applications. They're not always at a low temperature, of course. So the question is wondering what would be the challenges for NV center-based sensors at elevated temperatures, and which would be most appropriate for these elevated temperatures. And you're talking about 100 to 150 degrees Celsius.
So that's a good question that I'm afraid I'm not expert enough in NV centers to answer. I know that they work in ambient conditions. I know there are commercial enterprises already selling you NV sensors and, kind of in the box NV microscopes, working essentially under ambient conditions. I don't know how high in temperature they can go and what can start to go wrong as you increase the temperature. That's an excellent question, and I would refer the questioner to experts in the field like Christian Degen or Patrick Malatinsky or Jörg Wachtrup.
Another question, have you directly compared transport with local measurements on a single sample?
So I think that was very similar to the question that Jelena asked me when you were away, and yes, so we have done that.
Great, good to hear that. And another one, it was about noise, so nano amps per square hertz are possible. What about picoamps? Can you get there?
Yeah. Right. So let's see. I can try to go maybe to the slide here. So you can see nanoamps are already quite challenging, and only scanning SQUID is according to my sort of rough drawing here, is able to get to that level, and not with a especially high spatial resolution. So you need rather big sensors on the order of a micron or so in diameter. Going to much lower looks very challenging. Certainly picoamps looks extremely challenging to me, maybe not even possible. What I haven't drawn here, there are some theories about what is essentially the limit here of how high a combined spatial resolution and magnetic field sensitivity you can have, and that line kind of would preclude you to measure picoamps. This is based on some there are whole review papers on this, but it's based on some idea of a limiting energy density that you can reach, and so I think picoamps are probably not in the cards.
Okay, another cutting-edge question. The questioner wonders, can you comment on the dynamics of these and other techniques, which I think he means doing measurements in the time domain as well as the space domain?
Yeah, that's an excellent question. So, which I didn't really have time to get into. So, for instance, MFM, I mean, what I'm showing is essentially measurements of frequency shift, which essentially can be DC, but they can also be at higher frequencies. In general, you don't have a great bandwidth with mechanical sensors that you can investigate. You can measure kind of at low frequencies near DC, or you can measure on the mechanical resonance, which is usually quite limited by the whatever structure you have. So for a standard MFM lever, that's a kind of a few hundred kilohertz or so, and you can measure at that frequency and not really anywhere else. So the sensor is essentially like a very, very good bandpass filter and only reacts at certain frequencies. For the SQUIDs, I think the bandwidth there is really very good. You need to stay away from DC, where you have a lot of 1/f noise, but once you get into the sort of tens of kilohertz or beyond, you should be in the white noise limit and have very low noise, and essentially be unlimited in the kinds of frequencies that you can measure. For NV magnetometry, you can measure certainly at DC and at higher frequencies. They use some pulse sequences, so basically Hartmann, some kind of spin echo-like pulse sequences to reduce noise and get the lowest, get the best sensitivities, and that limits the frequencies that you can work at a little bit, but those in general have more, let's say, bandwidth than mechanical sensors. So I would say on the scale here, bandwidth is best maybe for the SQUIDs, then for the NVs, and worst for the force sensors.
So that, I think, is our last question. It was a really interesting one. So thanks everyone for tuning in, and if your question wasn't answered, look out for an email. Okay, bye everyone.
Thank you very much.